Welcome to another session of this video lecture series on Applied Physics UPH 004 course. In this series, we are talking about thin film interference, and today we'll talk about some of the application of this thin film interference and some common questions. For example, we'll talk about non-reflecting or anti-reflecting coating, why the center of Newton's rings appears dark in reflected light, why an excessively thin parallel film appears black, and why the camera lenses appears to have a blue-violet tinge. Now, in general, the application of the thin film interference is mostly for dealing with optical instruments like cameras. Example is here where there is this camera lens and you can see there is a particular violet tinge on the surface, and this is due to a special coating that is placed on the surface of the lens. We'll talk about this in little detail in the later part of this video. Here is another application of thin film, and this is for defrosting coating on the surfaces of this cockpit windshield. Let us now talk about why the center of Newton's rings appears dark in reflected light. For example, here is a Newton's ring that you see for transmitted light. Here is an example of the Newton's ring that you see in case of a reflected light. So when we say transmitted light or reflected light, what do we mean? So here is a plano-convex lens setup. So there is this glass plate at the bottom, and then there is this plano-convex lens, and this incident light is coming, and then two rays gets reflected, one from the lower surface of the plano-convex lens and another that gets reflected from the top surface of the bottom glass plate. So these two rays are the reflected rays, and when they interfere, this is the case of the Newton's ring with the reflected light. On the other hand, if you look at the plano-convex lens from the bottom, so in that case, these are the two transmitted lights. One that is gets transmitted directly from here, another, this transmitted light then gets reflected from here, and then ultimately these are the two rays which would interfere and produce either bright or dark fringes. So if when we consider such light, this is called the interference due to transmitted light, and when you consider these lights, then you call this interference due to the reflected light. So the question is that if we take these reflected lights, then the center of the Newton's ring becomes dark, while on the other hand, if we look at the interference due to these lights, transmitted lights, then it would appear bright. Why is so? So to understand this, it's not that complicated. So we have the path difference between these two rays, R1 and R2, is 2 mu d cos r plus theta plus lambda by 2. That's what we derived in our previous lectures. So this is the path difference between ray R1 and R2. What is the path difference between these two ray T1 and T2? In that case, this is, so this component which is there here, it's lambda by 2, here it's 0. There is no phase difference between the two rays T1 and T2, transmitted rays, and that's why there is not this extra path difference, while for the two reflected rays R1 and R2 there is a extra path difference, lambda by 2. Now at the center, so center means somewhere here. So at the center, this d is equal to 0 at the center. So when d is equal to 0 at the center, then this term is 0 and this term is also 0. So in case of the reflected two rays, there is still a path difference of lambda by 2. In case of transmitted rays, this path difference is 0. So when you see the interference due to the reflected light and those reflected light are coming from the center, then there is a path difference between them, and which is lambda by 2. So lambda by 2 path difference is equal to phase of pi between the two rays, and that's why when they interfere destructively. While on the other hand, for the two transmitted rays at the center, d is equal to 0, so the total path difference is 0, and that's why the rays that are getting transmitted from the center are in phase, and that's why they interfere constructively. So in case of reflected light at the center, destructive interference happens, and that's why the center is dark. On the other hand, in case of transmitted light, the path difference between the transmitted rays from the center, there is no phase difference between them, there is no path difference between them, and that's why they interfere constructively. That's why it appears to be bright at the center for the transmitted light. So these are the two cases, and this is the case of reflection due to transmitted light, and this is the case due to the reflected light. So now let's look at the next question that we want to talk about. So here is our next question, and that is why an excessively thin parallel film appears dark. A thin parallel film, excessively thin means when this T is very small. So if you look at the interference due to the reflected rays, then the path difference between, so this is the incident rays, these are the two reflected rays. So if you look at from the top, the path difference between the two rays 1 and 2 is given by 2 mu T cos R plus lambda by 2. So for excessively thin parallel film, T is very small, so this quantity becomes very small. And then the path difference between the ray 1 and 2 is only lambda by 2. Lambda by 2 means a phase difference of pi. So you know, when two rays having a path difference of lambda by 2 or a phase difference of pi interfere, they produce a dark fringe. So here, in case of a excessively thin parallel film, that means when the thickness of the parallel film is very, very small, then for the reflected light, the destructive interference occurs, and you see no light is coming out of this thin film, and that's why it appears dark. So that's our second question. So the third question is, what are non-reflecting or anti-reflecting coatings? Coatings are applied over a particular surface. So let's say there is a material, let's say that's a glass plate for our convenience, and on top of it you have a coating. So question is, what are non-reflecting or anti-reflecting coating? Obviously, as the name suggests, the anti-reflecting or non-reflecting coatings are those which, when applied over a surface, it doesn't allow any light to get reflected. In other words, if you apply this coating over this surface and there is some incident light on it, then most of the light either gets transmitted or absorbed in the material, and none of them get reflected. So no reflection occurs. So anti-reflecting or non-reflecting. So when would that happen? Now, to understand that, let's think about what is the situation we have. Let's say this is the thickness of this film, and that thickness is T. So in that case, any light which is incident on this surface, part of it gets reflected and part of it gets transmitted for simplicity. So when the lights are getting reflected, then if I choose this thickness to be such that reflected lights form a destructive interference on this surface of the thin film or surface of this coating, then that would mean no light is getting reflected. So non-reflecting or anti-reflecting means destructive interference. So in other words, what are non-reflecting or anti-reflective coating? So these are the coating which are applied over a surface with a particular thickness that results into no light getting reflected from the surface, and they do undergo a destructive interference over its surface. So that's about the non-reflecting and anti-reflecting coatings. Now let's look at the next question. So here is our next question. Why the camera lenses appear to have a blue-violet tinge? So here is the picture that we had earlier. So here is a camera lens, and this has this blue-violet tinge that you can see. Now the question is why that happens. Now the reason for this blue-violet tinge is actually there in the last question. Now to understand this, let's consider this following figure. Here, this is the lens surface. This is made up of glass, and over this lens we have this coating. So the refractive index of the lens is 1.5 glass. The refractive index of this coating is 1.3, and the air which is outside has a refractive index of 1. So that means we have chosen this coating material to be such that its refractive index lies between somewhere more than the refractive index of the air and less than the refractive index of the glass. So in that case, what happens is when a light is coming in, so this is the incidental ray, let's say this is our ray number 0, then one part of it gets reflected from this point, let's say this is A, so this is ray number 1 which gets reflected. Another part of it gets reflected from this point, let's say this is B, and this second reflected ray. So the interference happens between these two rays 1 and 2. One gets reflected from point A, 2 get reflected from the point B. For the point A light which is coming from a rarer medium and getting reflected from a denser medium, the coating, then between the ray 0 incident ray and ray 1 there is a phase difference of pi. Similarly, for the part which gets transmitted within the coating, for this ray, when it gets reflected from the point B, it's coming from a rarer medium, which is the coating, refractive index 1.3, gets reflected from a denser medium, the glass, refractive index 1.5. In that case also, there is a phase difference between this ray AB and the ray 2 which gets reflected, and that phase difference is pi. So 1 and 2 both have now the same phase. Both of them are having a phase difference of pi with respect to the incident ray. So basically 1 and 2 now do not have any phase difference. In that case, the path difference now between the ray 1 and 2 is 2 mu d cos r only. Earlier we had here lambda by 2, but this path difference is not there at this moment. So this lambda by 2 situation comes when there is this coating. Let's say this is made up of glass, a denser material. This is air, this is air. So rarer, denser, rarer. On the other hand, here, this medium is rarer with respect to this medium. But again, this medium is rarer with respect to this medium. So when the reflection happens from this, it gets a phase difference of pi. When the reflection happens on this, again, it has a phase difference pi. On the other hand, if reflection happens from this, it has a phase difference of pi. But when the reflection happens from this, there is no phase difference here. The phase difference is 0. So that's why in this such a case, 1 and 2 has a resultant phase difference of pi. Here, there is no phase difference between 1 and 2 in this case. So once we have this 1 and 2 be in phase, so in that case, the path difference is only 2d mu cos r. If we consider that these rays are normal to the coating, then r is equal to 0. Mu is the refractive index of this medium, of this coating, so that's fixed. So only thing for us to control the path difference is this d. So when we apply a coating over this glass surface, then we apply the coating in such a way that this path difference, which is 2 mu d cos r, becomes is equal to lambda by 2. So for such coating, we choose this d to be such that this path difference 2 mu d cos r, which is nothing but is equal to lambda by 2. So choose this path difference so that the reflecting rays interfere destructively. So no light is getting out due to reflection. Now from here we can see that this cos r for normal incidence is equal to r is 0. So cos r is equal to 1. So this part is equal to 1. So we have 2 mu d is equal to lambda by 2. That would imply that you choose d to be is equal to lambda by 4 mu. Okay, so if we choose d, the thickness of this coating, to be is equal to lambda by 4 mu, then the path difference between the ray 1 and 2 would be lambda by 2, and that would imply that 1 and 2 interfere destructively. So non-reflecting coating. The next, for white light, it's not a monochromatic light. So there is no one single lambda wavelength. So which wavelength to choose? We choose generally the middle one. So in white light, we have this rainbow color, and for this rainbow color, the center is this green. So for a general purpose lens, we choose this d with this lambda to be is equal to the wavelength of the green light. So that means that this coating would be non-reflecting perfectly for the green light. So if it is non-reflecting for the green light, then we should not see the green light to be reflected. So okay, first thing, we don't see any green here. Then why do we see the violet or blue violet color here? That explanation would be like this. So if here we have assumed that there is a normal incidence of the light, but let's say it's not normal, it incident with some angle with respect to the coating, then in that case d would be 4 mu cos of r. So for not normal incident. So what is r? R is the refraction angle, and that depends on I, the incident angle. So that means now for not normal incident, this d increases by a factor of 1 over cos of r. So that's why we say that even if we choose this lambda to be the green color wavelength, still because of this factor, as the incident angle increases, this factor 1 over cos r also increases. And that's why the destructive interference becomes more complete for longer and longer wavelength. And because for longer wavelength with increased incident angle, the destructive interference becomes more complete. That's why less and less these higher wavelength lights are getting reflected. So if higher wavelength lights are not getting reflected, which one would get? This lower wavelength lights would be getting reflected. And that's why we see this blue violet tinge on this lens surface. Actually, this blue violet tinge, if you look carefully, would also change if you change your viewing angle. And that is because when you change your viewing angle, basically you are controlling this reflection angle, and that's how you are basically controlling the effective D which is there for the light. So that ends our last question, and this is the end of the video lecture. Thank you.